Niels Bohr Institute from University of Copenhagen. And she's also scientific advisor of the Miraculous Spectrometer project at the European Spallation source. So today she will talk about a really interesting question. Does Superman really have X-ray vision? So thank you, Heloísa, for being with us. And I hope that this talk will answer this question.
Thank you, Fanny. Thank you, everybody that is there to listen to my talk. I know that for some of you it's quite early in the morning, and for me it's lunchtime. So I hope that by the end of my talk, you are quite awake and you have some questions for me. So as Fanny mentioned, the title of my talk is Does Superman Really Have X-ray Vision? And I hope that by the middle of my talk, we can get an answer, and that by the end, we all agree with the answer that we got. So now, first I have to be able to change my slide. And then here, what I would like to start with is the time that we all fear is when we start listening to this sound. And then how does physics or X-rays or this other new particle that I'm going to introduce you is really part of our daily life? So one of the things is that tooth decay or caries is one of the oldest and most spread diseases in the world. And there is a lot of material science research to try to develop a better dental material. There is also a lot of research that will avoid that we have contact with needles. So what I do in my research most of the time is to try to look and really find out what is happening inside of matter when things are hidden. So most of the research I do is to understand how a molecule works under confinement. And that is the first topic that I'm going to describe to you. So if we think about, right, how do we see things? How does the dentist define if we have a tooth decay, a carie or not? So our eye only receives light. So first of all, there is not something like a vision ray that shoots to the eye. If Superman really had X-ray vision, how would it then work? Well, Superman would have to send X-rays to a material, and then we would have the interaction with the photons and the matter, and then it would be detected. So it means that Superman eyes would have at the same time to shoot X-rays and to detect the X-rays. So in real life, right, how does we use X-rays? So if we think about imaging, imaging means that we are really looking inside of matter. So when we need to take an X-rays of ourselves, what we will be basically observed are our bones, because the soft tissues, they are attenuated by the X-rays. Oh, sorry, the soft tissues attenuate the X-rays. So when my collaborator from the odontology faculty here in Copenhagen University looks, how does it look a tooth after she treated it with a dental material, with a dental cement? She will use what we call the convention X-rays. That's also what our dentist does to us when we go to have a dental treatment. And it looks beautiful and perfect. We can see here that we have this beautiful fit between what was fit in the tooth and the tooth itself. I lost my pointer, but I will try to explain to you what I want you to see. So you can see that in the image, this very dark part is the soft tissue that we have inside of the tooth. And then the soft tissue is protected by hydroxyapatite, that is the bone. So that's a little stronger, right, for the X-rays. So we have more electrons, so the X-rays can scatter better. And then we can see that we have this little square in there, and that comes from the cement that was put in the tooth. So we have a perfect filling. But we as researchers, we always want to understand better what is really going on. And to understand what is going better in this type of material, we need to use synchrotron X-rays. So we can use synchrotron X-rays imaging. And with synchrotron X-ray imaging, what we are able to do is that we can look inside of matter, and we can look at inside of smaller and determine smaller size. So when we take the same sample and we put in a synchrotron beam, and we do what we call the X-ray tomography, what we start observing is that this perfect filling, in fact, is a porous material. And we knew it because it's a cement, it's a dental cement. And to be able to cope with all the stress that we put when we masticate, and also the changes in temperature when we drink something very cold and then something very warm, we need to have some thermal dilatation of this material and being porous adapted. So it's fine. However, what was very surprising for us was to look at the X-ray tomography and see that we have very large pores. Okay, so then we go to the next step, that's what we want to understand a little more. We know that when we prepare this material, we have a silicate, that the dental cement powder itself, and we will mix that either with water or with a polymeric solution. So it means that when we have this powder and the liquid, the reason why this substance becomes now hard, but at the same time flexible, it's because of the amazing hydrogen bonds that are formed. So that is what makes the material harden. Then the question we had is like, okay, we want to see hydrogen, but as we mentioned in the very beginning, we are talking about something that is like the soft tissue, and X-rays is not the fantastic probe that we could use to observe these hydrogen bonds. So what do we have to do? We have to take now advantage of another technique. And this other technique is called neutron scattering. And why do we need to use neutron scattering in this case? Because neutron is a wave and a particle. So the neutron is a particle because it has mass, and it's a wave because it will have a momentum. And the neutron will interact now with the nuclei. And because it interacts in the nuclei, it will be able to tell you or us what the hydrogen atoms are doing in a system and where these hydrogen atoms are located, because as interact with the nuclei, we can take advantage of deuteration. So if we want to look at dynamics of hydrogen, we can work with the sample fully hydrogenate. And if we want to look at a structural information on the sample, we will deuterate this sample because we have this power for the isotopic substitution with neutrons. So what we have to remember is that now, because neutrons are waves that interfere with atoms and that are particles that we can use to detect them, we are using quantum mechanics, right? And we can use, in this case, the wave-particle duality that is the Copenhagen interpretation. So then what happens when we take the same sample and we put this sample now in a neutron instrument and we take an image and we make a tomography, we are able to observe that some of these pores are filled with liquid. as we can see here by this very high contrast that is in red on the figure that I'm showing to you, the neutron tomography. And because we had the same sample in all cases, it's just rotated in relation to the conventional X-rays, we were able to really make these images compared to each other. And what we could locate is that the big pores that we could observe with X-ray tomography are filled with liquid. And why is it bad? It's because water will then diffuse. Water is now, or the liquid, the trapped polymer, is now able to diffuse and move through this material, and that's what creates cracks. So in the same way that sometimes we have to go back to the dentist and change the filling, we have the same problem in our houses when we start observing cracks in the wall. So it's not exactly the same material, of course, because we are talking about construction, cement or dental cement, but the physical principle is the same. We have porous materials that have liquid trapped in them. And then what we can also do with tomography, and in this case, what I'm showing to you here is the analysis of the neutron tomography, is that we have this huge distribution of pores. So small pores would be fine. Big pores are a problem because they are prone to trap liquid, and also they are prone to create weaknesses in some parts of the sample. So the other thing is that neutron scattering can tell us about the structure. So we can solve, for example, as we saw the imaging, we can also solve protein structures without being able to locate the hydrogens. So the hydrogens are inferred. If we want to solve really a full protein structure, what we would do then is that we would take advantage of deuteration, deuterate this protein, use the very high resolution structural information that we can get with X-rays, get the position of the heavy elements, fix this position in the structure, now do the same analysis using neutrons with the deuterated sample, and then position the hydrogen atoms. It's not very easy, it's very challenging, but it's possible to do. So neutrons can also tell us about dynamics because we can observe change in momentum transfer. So what I'm showing to you here is one of the techniques that I use quite often in my research. That is the figure on the bottom there, is the spectra where we can see an intensity and an energy, and that's what we call quasi-elastic neutron scattering. So quasi-elastic neutron scattering means that we are observing very, very tiny changes in energy. And what they do is that they will create a broadening that is most of the time analyzed using a Lorentzian function. And analyzing this Lorentzian function, we can, for example, as I mentioned to you, obtain information about the water that is trapped inside of this porous material. So here I put for you different pictures of neutron instrumentations that you can have an idea of how large these instruments are. So on the round thing, the blue thing, it's what we call the backscattering instrument. On the top, just for you to have an idea, we have a person, so you can have an idea of the size. The figure on the bottom is the inside of these instruments, so they are silicon analyzers. And what is going to happen here is that the neutrons are going to come through the neutron guide, that is this dark blue thing that you can see on the top figure. You will heat the sample that is inside of the cryostat that you can see in the bottom. It will interact with the sample. It will then be scattered and interact with the silicon analyzer, backscattered and detected, and we can obtain the spectra that I'm showing to you. On the top, what I'm showing to you now, it's a detector that is put in a powder diffractometer in a facility in the United Kingdom. And the figure there, it is Marcella, my former PhD student, mounting a sample. So you can see that we have this huge instrument and the samples about 3 by 3 centimeters, and normally we used about 1 gram of sample. We can also do with milligrams. Oh, and then, sorry, what we can do also to understand this data is that we can do some molecular dynamics simulations. So here it's an interpretation of the dental cement liquid that was used. So we have the polymer chain, that is the dark molecules, and we can see that these pink molecules are water molecules. So what happens in this liquid is that some liquid will be trapped when this polymer entangles. Some of liquid will not react at all, so it will be basically bulk water, and some of this bulk water is very much connected to the polymer. And doing this analysis using different instruments, so during the quasi-elastic analysis using different instruments, we are able to obtain information in all these types of liquid. So to recap, when we do X-ray experiments, what we have is that the intensity of the measurement that we are doing will vary with the atomic number. And that is why it is very difficult to detect samples that have hydrogen or lithium, for example, in them. When we use neutron scattering, the neutron particle and wave will interact with the nuclei, and that's what we can see in the bottom. And this interaction is what we call the cross-section, is very large for hydrogen. Another advantage, for example, when we are looking at battery systems that have lithium, neutron is also a very good probe. So I hope that by now we can believe that X-rays, Superman does not have X-ray vision, but Superman has neutron vision. Why? Because we need a particle that is deeply penetrating to go through the wall, what neutron is, and we need a particle that is able to interact with the hydrogen, soft material. The only problem that we have here is that, as we said in the beginning, the eye would have then to act at the same time as the producer of photons or neutrons and the detector for these interactions. So I'm just going to give to you a very brief crash course in neutron scattering. So then after my lecture, you can consider yourselves expert level 1 in neutron scattering. So when we talk about neutron scattering, we always talk about scattering length. So when we consider X-rays, what happens is that in X-rays, the photons will scatter from the electrons around the nuclei. So when we observe this scattering length, it will have a formal factor, and the scattering length will then depend on the scattering angle. That is the line that we have as a continuous line in there. As the neutrons scatter from the nuclei itself, and it's a much smaller object, it has no form factor. And when we talk about magnetic scattering, that is another way that we can use neutrons, because neutrons have a spin. And if we want to determine the spin of a sample, we will have this interaction between spins, and then we can define if a structure is magnetic, ferromagnetic, or antiferromagnetic, and we can also analyze spin waves and magnons. So because the magnetic neutron scattering will interact with outpaired electrons, we will then have a form factor as well. So when we talk about scattering cross-sections, we will talk about coherent cross-section. When we're talking about single differential cross-section, we are talking about structure. So in the Q and omega space, what we are going to observe is a Bragg peak in a very defined Q vector value. And in the real space, what we see is the atoms distributed in a lattice. If we have incoherent scattering when we're talking about structure, so for example, as mentioned to you, if we have a protein, because we have a lot of hydrogen, this hydrogen will create for us some incoherent scattering, and that is translated by background in my Q and omega space. And that can also be from paramagnetic scattering, for example. So at room temperature, we can have a material that is in the paramagnetic state. When we cool it and the system orders magnetically, we will observe then a magnetic peak. And what happens is that this background will then transform in coherent magnetic scattering. When we're talking about dynamics, what we have is that we have a change in momentum or angle and a moment and energy. So we're talking about double differential cross-section. So if we have a phonon, so we have the lattice, all the atoms are vibrating coherently, we will have what we call an elastic vibration, and that is coherent. If we have, in the case of water diffusion, that it's a self-diffusion and one molecule does not need to follow what the other one is doing, we have quasi-elastic scattering. So what we measure at the end, we will collect neutrons in neutrons per second in the detector. This intensity is fully proportional to the sample that we are measuring. So neutron is a very quantitative measurement because the intensity is directly proportional of the number of elements that we have in the scattering volume. This intensity is also proportional to the neutron flux, to the angle, and that is why we have these huge detectors, and to the energy window of the instrument. And of course, the only way that we have to improve that is to try to build sources that have more flux, or to increase the number of detectors and the size of detectors. Neutrons can be produced in two ways, either by fission, that what happens is that we are going to have a slow neutron that is going to hit an element like uranium-235. We will have then fission. We will produce, in this case, 2 to 3 neutrons per fission, and then 1 neutron will be used to continue in the cascade. And in this case, we can have reactors that are around 20 to 50 megawatts, research reactors. So we are nowadays on the top of what we can have, and what hinders us to producing more neutrons in a research reactor is that we need to moderate these neutrons to be able to do research with them. And that is what we have in a swimming pool in a research reactor. And what we have here, we have the reaction, and then we will moderate this fission reactor with water. So we have this swimming pool, and what we can see there on the bottom are the different channels that will then create the neutron guides that will then direct the neutrons to the instrumentation we have. We can also produce neutrons using spallation. So that is the idea of the European spallation source. It is a much more expensive reaction, in fact, but we can produce about 30 neutrons per proton. So we have now a cascade that is much more efficient. So I have a little movie for you to watch, and it's to show to you how these neutrons are produced here in Sweden. Well, in fact, European spallation source should come to life in 2025. So how we produce this neutron to study materials on the atomic level? We will have to build, first of all, an accelerator. So we need a very powerful accelerator that is very long, and that is the line that you can see there. We are then going to use this very fast protons that are going to hit now a rotating helium-cooled tungsten target that will then be moderated to get to the energies that we can use to do our experiments. These moderated neutrons are then going to be tunneled into different neutron guides. And at the end of these neutron guides, we can build different instruments that are adapted to do different research. So this is a quite old figure by now of the construction site in Sweden. And Miracles is the instrument that I designed together with a colleague that passed away a few years ago. And now it is being built by a Spanish crew. And I always like to say that miracles do happen, but it's very expensive. So just for you to have an idea of the cost of a neutron instrument at the European Spallation source, this is about 14 million euros. But miracles will be very different instrument because we will be able to do dynamics or quasi-elastic neutron scattering experiments on covering picoseconds to nanoseconds. So just for you to have an idea, nowadays to understand the dynamics of the liquid that we used in the dental cement, we had to go to 3 countries and use 3 different instruments. And in the near future, it will not be needed anymore. We can go to miracles and do this experiment in a single instrument. So now that we know what neutrons are about, so it's a large scale facility like LNLS in Campina. So we make a sample, we write a proposal. Once this proposal is accepted, we do our measurement. We have to write it up, and then we either get a patent or we have a publication. The neutron landscape today is quite small. So we have very good reactors in Australia. The ILL reactor is the best one in the world. The one in Germany that I worked for a couple of years closed last year, 1 year ago now. SNS is a Spallation neutron source in the US, is the best neutron facility nowadays. ISIS is another one. It's one of the first ones, and they are going for a big upgrade. ISIS is very close to diamond, and if you can see there, you can see that both ILL and ISIS, they have the same layout. So you have the neutron together with a synchrotron facility because they are very complementary techniques. Then we have the newest Spallation source, that's J-Park in Japan. So there are 2 new projects for reactors. One is in Arama in Brazil that was approved and hopefully will get ahead into construction in the next years. And the other one is the reactor in Argentina that, for what I know, is already in quite developed stage. And the European Spallation source in Sweden. So this is my last slide on the crash course. So what we have really in neutrons, we have a source, so either fission or spallation. Neutrons are then produced in all colors, wavelengths, and directions. To be able to use them, we need to use a monochromator or a polarizer. So in this way, we can define the neutron initial state, momentum, energy, and spin. The neutron will then interact with the sample and produce the data that we want, imaging, inelastic results, so structure. And then it will be scattered again in different states. It will then be analyzed, and only the neutrons that are in the final state that are needed, or they are within the window that we want to measure, will come to the detector. So at the end, we pay a very high price because we need to filter neutrons twice. So neutron scattering is signal limited. It is very expensive. We can only measure that, obtain our data in very field dedicated facilities. We have to go to a proposal review. So my advice to you is that never use neutron if any other technique can give to you equally good scientific information. However, sometimes neutron scattering is the only way to get the information you need. So now you can consider yourselves neutron scatters expert level 1. And we are going to move to the other part of my talk. And on this slide, I made a very compact slide because it's an information of the different researches that we are doing here in my group at the Niels Bohr Institute, in collaboration with many different groups in different parts of the world. So the dental cement is the example that I gave to you first. We also study pharmaceuticals, either pharmaceuticals by themselves to understand, for example, polymorphism or conformation, or also pharmaceuticals that were encapsulated in different carriers, such as clays or sugars or lipids. We also look at cancer cells. So what happens, what makes cancer cells differently from health cells, and what happens with cancer cells when they interact with a drug. And in this case, what we are really interested is how water changes in these different environments. We also have a new project in porous organic polymers, and this project is together with Professor Rodrigo Lima from the organizer committee. And our paper is coming online quite soon, and it's a quite cute research where we can observe that by doing very clever chemistry, we can develop a new material that can not only capture ammonia, but also keep ammonia connected to it. So again, hydrogen bonds. And this is very important for filters or for pollution in general. We also study clay systems because clays are materials that are used a lot. So, for example, for radioactive waste management or also for drug delivery. And what again is very, for CO2 storage. And again, what is very important in these materials is to understand the hydrogen dynamics. So it's to understand how a clay is hydrated, so how water comes in and how water comes out. We don't want to have this motion when, for example, we use clays to keep radioactive waste. We all know that depending if we have some hydrogenous species in the clay's interlayers, we are able to absorb CO2. And the clays have been used as medicine for ages and ages. So now we are going back again to use clays as antibiotic carriers, for example. So as I said, we already discussed about the dental cements and why dental cement crack. And now I am going to tell you about the research that I have developed for the last years together with the University of São Paulo and the Butantan Institute. So it's the idea of needleless-free vaccines. So just, I want to make a statement before I continue my talk that I am not here to defend vaccination. I'm not telling neither you or your children to get vaccinated. I am only going to present to you scientific facts. So our first study on needleless vaccines is for the delivery of hepatitis B. Hepatitis B is a virus infection that attacks the liver and can cause acute or chronic disease. It is an important occupational hazard for health workers, and it is estimated that about 204 million people are chronically infected with hepatitis B. Hepatitis B has no cure, but hepatitis B can be prevented by a very effective vaccine. So here I just put a sketch for you to know how hepatitis B can be transmitted. And on the top there, we have a geographic distribution of hepatitis B infection. So we can see that in some areas in South America and Africa, we still have a very high concentration of hepatitis B, and we also have a very intermediate concentration of hepatitis B. So why, if we have a vaccine that is very efficient, why should we try to make things better? Well, first of all, is that we can always improve immunological response. The idea of avoiding needle trauma is very important. And also, if we have an oral vaccine, we do not need specialized healthcare workers. What makes this distribution and the cost much less. And the other issue is that, as we have heard in the media these last days, we need always to store vaccines at lower temperature. So in the case of the hepatitis B vaccine that is produced in the Butantan Institute, to be delivered in the Amazon regions, for example, it's transported inside of trucks that have fridge, and the temperature of these trucks is monitored constantly, and the vaccine cannot go above 4 Celsius. So if anything happens, that the truck breaks or something, all the loading of the vaccine is lost. So if the vaccine is stored in some area that we don't have electricity and the fridges went down, that vaccine is not effective anymore. So the idea here is that if we encapsulate the antigen, so the surface antigen for hepatitis B is called HBsAg. So if we encapsulate the antigen, that is a protein that has a diameter of about 25 nanometers, we will then be able to protect the antigen because it will not deteriorate, and we can also deliver it orally. So one of the ideas is to encapsulate this antigen in what we call SBA15, that is a Silica Santa Barbara amorphous, and it was developed in Santa Barbara, and that's where the name comes from. So the SBA particle is divided in these particles that are about 20 microns, or 20 microns in general, right? So that's the whole particle. This particle will then have micropores. And then we have these little, we can think like about straws. These straws are 2 micron longs. And inside of these straws, we have a very beautiful hexagonal ordered mesopore structure, where the diameter is about 10 nanometers. So that is what SBA looks like. A very nice type or example of material that we need many different techniques to study the structure. So the question that was posed to us is that my collaborators in Brazil, they know that this vaccine is effective because they had done many tests on it. However, they still had questions in how the SBA protects the protein, how this protein is distributed inside of the SBA, and why the optimal ratio, biological optimal ratio, is 1:40. So this and the other questions are the ones that came to us. So to answer these questions, we use 2 different approaches. We used X-rays and neutron imaging techniques. So what we did here is that we extended the knowledge that we had acquired in the dental materials to help answer the questions that were posed. Here in the bottom, what I'm showing to you the different collaborators that we had in this different instrumentation. So in Berlin, we did the X-ray attenuation tomography and the neutron attenuation tomography. We went to ESRF to do the phase contrast, and I will not have time to talk to you about the X-ray absorption measurements that we did in Switzerland. So here, if I show to you these two photographs, right, or these two images, showing the distribution of the protein inside of the silicate, and I just switch them around, it will be very difficult to distinguish them. So what we are looking at? We are looking on the left side at the X-ray distribution, and remember, with X-rays, we are interacting with the electrons, so we are observing just the heavy elements. And with neutron attenuation, we should be observing the protein, the hydrogen. So the first thing that was very surprising to us was the fact that we saw so much structure on the X-ray tomography. We were not expecting that. So that can be explained that when we, to encapsulate this protein, we need to use a salt. So we use a saline solution. It's a buffer saline solution where we have sodium and we have phosphorus as the main components. And these are heavy elements that the X-ray attenuation tomography could capture. So in the X-ray tomography, what we are observing is the distribution of the salt in these grains. When we take the same slice with the neutron tomography, what we are seeing now is how this protein is distributed in these grains. So what we see here is that the protein agglomerates with the salt, and the protein, neither the protein nor the salt are uniformly distributed. So if I just go back here, and we see this arrow there, so my student was very lucky that he could find this same particle, because it's the same sample, we just moved the instruments. And he found this particle, and he made a movie of this particle where he put together the X-rays and the neutron imaging together. And that's the movie what we're going to see here. And what you see, I hope that the resolution is good enough, that you can see that in blue is what we got from the X-ray tomography, and the pink is what we got from the neutron tomography. So in pink is the protein distribution. And if we look around, we can see that the protein is located exactly where we have the salt. Then we did the same exercise for different concentrations of silicate to the protein. And what we can see here, that remember I told you that we have this magical number 1 to 40 is where we had the most biological activity. And interesting, it is also the ratio where we have the least agglomeration of proteins. How we can understand that? That the fact that when a protein agglomerates, it loses functionality, right? So that was a very interesting observation, that we still are far away from having a sample where we have a real uniform distribution, and we still have problems with agglomeration. So, but then we really want to understand where is this protein? Because remember that I mentioned to you, the protein has a diameter of 25 nanometers. And the mesopore structure has these spores that are these tubes that are 10 nanometers. So the protein cannot be protected inside of the hexagonal structure. It has to be somewhere else. So we went now to do X-ray phase contrast with very high spatial resolution that we cannot achieve with neutrons. And we really want to look at the grains. So now here, what we see is that we see the SBA 15. We can observe the location of the macropores. We can now see where the salt is located in these macropores, because we know from previous analysis that where we have salt, we will have protein. So we can locate the distribution of protein and salt as well. And now what we're going to do is that we are going to take one of these elements with a micropore, and we are going to make slices in this picture, so we can make some transparency here. And what we can see now is that this protein, together with the salt, is in fact protected inside of these micropores. So the other question we wanted to answer, and I think I still have a few minutes to go on that with you, is to understand the dynamics of the encapsulated protein. So for that, we did a quasi-elastic neutron scattering experiment. And again, we had to use two different instruments. So we went in this time to SNS, that is the blue machine. And we also went to Australia, that is the white instrument in the side. So what we got from here is that we can get a diffusion coefficient. And we can also get an indirect location of the protein. So what we conclude is that, first of all, we know what is the diffusion coefficient of bulk water. And by doing an analysis that I don't have the time to explain to you everything, we can get the diffusion coefficient for the salt and for the protein. So we have a diffusion coefficient that is much smaller in both cases. So it confirms to us that we have this salt and this protein plus salt confined in the structure. We can also get a mean square jump length. It means that from where the water molecule is going plus the protein is going inside of the structure. And we can see that this mean square jump length is comparable in both cases. So what means also is that this confirms our imaging data that the protein is located where the salt is located. So I want now to summarize my talk. So from the analysis of X-ray microscopy together with neutron X-ray tomography, we were able to observe how this antigen is distributed inside of the SBA15. It is distributed inside of the micropores. And we also know that the diffusion of the protein is slowed down. So it means that when it goes into our body and it has contact with our own fluids, it will help the protein calm down and will immunize our system. We are now moving to diphtheria, anatoxin. We have a paper that was just accepted. And the case here is quite different because when we talk about anatoxin, we're talking about much smaller proteins, if you like, and it's 10 nanometers. So in the way that it is protected by the SBA15 is very different. So I would like to thank my colleagues from USP and from all around the world that had contributed to the work in the vaccines we did. I also would like to thank my colleagues from all around the world that have contributed to the many different researches that we developed in the group that I touched very briefly. And I want to conclude that does Superman really have X-ray vision? No, Superman has neutron vision. Thank you.
Thank you very much, Heloísa, for this really interesting talk. And now we know the answer about Superman. So thank you very much for this. Well, actually, for all this information. So the session is open for question. You can either raise hand on the participant or either on the question and answer chat. And so actually we have a first one from Victor Lima. He says, thank you for the excellent presentation. Is there a lot of difference between sample preparation for X-ray tomography and neutron tomography? which is more difficult?
We use exactly the same samples. So no, there is no difficulty. What was difficult was to get the high resolution X-ray data, because then we had to put this in very tiny capillaries, and it was a little complicated. Otherwise, it's not a problem.
There's another part of this question still of Victor. Is asking, in a quasi-elastic neutron scattering experiment, is it possible to have information about energy transfer, or it's only momentum?
No, you can also have information on energy transfer. So, for example, if you have tunneling, you can look at that. It's very interesting if you're looking, for example, at molecular magnetism. You can also have information on magnons or spin waves.
Another question from now Diego Guzman. He says, thanks for your presentation. I have a curiosity. How can we direct accelerate or deaccelerate neutrons so as not to destroy the samples? There's two parts. How are the images generated in the case of tomography, or how does the detectors work?
Okay, so what happens is that we have to moderate neutrons, and most of the time we use water as a moderator. So to get the energy to the energies that we have in condensed matter systems, right? And in this case, it will not destroy the sample because we are not generating energy. So sometimes we have some problems with biological samples with X-rays that will not have with neutrons. However, if we want to deuterate, we can kill a sample by deuterating, right? So you have to be careful in that way. How we normally use helium detectors to detect the neutrons. And in the case of the tomography, we use scintillate detectors.
Yes, I'm looking. There was a perfect. I have one. I have a question, really large question, because you showed that there's really few neutrons facility around the world, and my question is, why? Is it really the cost that is the main problem, or is there another technical problems, or the demand is still low?
Well, the demand is not low. We have sometimes instruments that are oversubscribed by a factor 40. So that is. What happens is that it's a very expensive technique, and neutrons is a reactor-based research. And nowadays, nuclear physics is not very popular. Right? So that is one issue. And that is why we are moving more to the spallation sources.
So you think that in the future, actually, so you showed that there's some news facility that are building, but normally they will not, it will always be few facilities. It will never take the market.
Yeah, now we are trying to develop what we call the condensed neutron sources. That is something that you could have in your lab. So you will do very preliminary work in your lab, but it is possible, right? So in Japan, for example, they have what they call the portable neutron sources, and they survey roads. They survey the quality of asphalt using these portable neutron sources. So that is also the way we are going. Not as much powerful, but to do very specific. So imaging and science.
Perfect. So I will see in the future. Another question about dimension of the sample and the resolution. My first question is, what is the maximum of thickness of the sample that you can use? Because a teeth is kind of really, really thick. So
Yeah.
what is the maximum?
So neutron penetrates very deeply in matter, right? So that you have, for example, companies that will take a whole car turbine, put in a machine, and look how the oil is lubricating the car, right? So we don't have. We have a problem though with hydrogen, because hydrogen attenuates, right? So if you have a sample that is with a lot of hydrogen, then we have to have very fine samples. But as the tooth has hydroxyapatite, it's okay, for example, to go in. And metallic samples are also fine.
Perfect. So we can...
Yes. And resolution-wise, to do imaging, the best we can do nowadays is 6 microns.
6 microns?
The resolution for imaging, yes, 6 microns.
And so sometimes it may be, it's not enough precise to be able to see what we want to see.
Exactly. But, for example, if we want to go to very higher resolutions, we have, for example, for the tooth, we cannot do that because we would need very high times of exposure. So although we would love to do X-ray tomography, high resolution X-ray tomography, we can't because we would dehydrate the tooth because it takes too long.
So it will...
yeah, so it is, cannot have everything. Yes.
If the tooth at the beginning is not the same as the end, then yes,
yes.
there's a problem. Perfect. Well, a last question about like really curiosity. So how much time do you have for the experiment? So in a full year, how much day that you were able to spend at the neutron reactor to really acquire the data?
Okay, so it depends on the sample. So if you want to do small angle neutron scattering, it's very fast. So they have sample changer and you can kind of collect like 24 samples in a day. It's fast for neutrons, right? When you do quasi-elastic neutron scattering, you may need 6 hours per temperature if you want to do temperature. Sometimes you need 1 day per sample. So it's really depending on the technique, on the sample, on the size. The imaging, we did very fast. We did the imaging in something like half a day, the whole tomography, right? So the whole rotation for the tomography.
Yeah, so it's a lot of time.
It is a lot. Compared to X-rays, it is a lot of time. Even compared to Raman spectroscopy now, yes, it's a lot of time.
But it was the price.
Yes.
So perfect. So well, thank you again for your nice presentation, for your time and the nice presentation. It seems that really everybody enjoyed it, and now we are all specialists about neutron scattering.
Thank you. Bye.
Thank you very much. So now our next speaker will be Túlio Rocha. Actually, we will switch from X-ray tomography to X-ray spectroscopy, and we will switch from soft tissue to hard material. So Túlio is a specialist in X-ray spectroscopy, applied mainly in condensed matter materials and energy materials, and in particular for the link between macroscopic properties and the atomic structure and the electronic properties of the materials. He was a PhD at the Unicamp University, so the University of Campina in Brazil, and is now a researcher scientist as a new beamline of the new synchrotron. The new synchrotron light that we have in Campinas, which is part of the Brazilian synchrotron light laboratory, which is called, the new synchrotron is called Sirius, and is the leader of the beamline that is called IP, which stands from inelastic and photon electron spectroscopy. So it will be a beamline that is completely dedicated for these techniques. And today we'll talk about unraveling the structure of matter with synchrotron light. So Túlio, I don't know if yeah.
Oh, thank you very much for the introduction. Can I present here? Let's see. Can you see my screen?
Yep. Can just put in the presentation mode.
It's coming.
We have the presentation, but we see the slide and the next slide.
Sorry.
So we already know
it's the two screens. It's the two screen problem. I'll try again.
Otherwise, we will
Yeah.
we will know the punch. It's still the
No spoilers. Oh, what's happening? I have to leave the PowerPoint.
It's part of our technical problems, and from my experience, Zoom and Google Meet doesn't like to have two screens. You never know
Exactly.
what is presented.
Sometimes it works, other times it doesn't.
Now, it's
do you see? Now let's see if it's
perfect.
perfect. Okay. Well, first of all, thank you very much for the invitation to the organizers. It's a pleasure to talk about Sirius to the Brazilian community and the other viewers from different parts of the world. So my talk today is about how we can use the synchrotron light sources to study the structure of matter, particularly condensed matter. And to begin, this is outlook of my talk. I'll talk about what is CNP and LNLS, a little bit about the structure of matter. That's what we want to investigate. What is synchrotron light and what's special about Sirius light source, this new facility we built here in Campinas. A little bit of the light matter interaction and the techniques that you can use to study the structure of matter. And in the end, show some examples from the literature, okay? So to begin, CNP is the Center for Research on Energy and Materials located here in Campinas. It's a large center. It's a non-profit organization that works under a contract with the Ministry of Science and Technology and Innovation. The CNP is formed by 4 national labs: the Nanotechnology National Lab, Biotechnology National Lab, the Biorenewables National Lab, and the Synchrotron National Lab. That is where I work. And the LNLS was operating the UVX light source since 1997, and now we are operating Sirius, this new 4th generation light source that is coming in operation. Okay. And the main question that I want to answer is to make you understand why we build these big machines. So they are huge instruments, so it's a factory size, costs billions, and demands a lot of people to operate. Nevertheless, we have more than 50 instruments like this all over the world. So the question is why so many countries, especially the developing countries, if you see here in Europe, North America, and Asia, you see how many synchrotron sources they have. It's important. So it's important because it's one of the most powerful tools to study the structure of matter. Okay, and it's very complementary to other techniques that you can use in your own lab, different kinds of spectroscopy, and also other big facilities like Neutron facilities that we heard from Heloísa a few moments ago. So now I want to talk a little bit about what's what's structure, what I mean by structure of matter. So structure is something we observe in the nature with our visible eyes. So observing structures in living beings, it allows us to do classification. So we classified animals and plants. And this, for instance, was extremely important to better understand the world around us. This was what inspired the theory of evolution, looking at the similarities, structural similarities. So it gives ideas about origin and also gives idea about functions. And nowadays, for instance, what you can do is to use artificial intelligence in your phone. You take a picture of a leaf of a plant and you can identify this plant just looking at structures. So on this leaf. So structural characterization is something very important, and it's a main paradigm in science. It's something we use for a long time. If you look at the smaller scales, nature has structures from this macroscopic all the way down to the atomic scale. So if you look at your finger, you have the fingerprints, you have the tissues, cells, the organelles inside the cells, these ribosomes here that are these molecular machines. So if you look inside the ribosome, you have these proteins. Inside the proteins, you have these amino acids. All of them show structure. So structure is something that happens at different scales. Okay, and if you look up at bigger scales, you see structures from the solar system to the galaxies, all the way to these clusters of the superclusters of galaxies that are 100 million light years large. So we see structures in nature in all scales. Okay, and one of the main questions is that even stuff that we don't know yet what it is exactly, like dark matter, it shows a structure. So we can see that the dark matter is not homogeneously distributed in space using gravitational lensings. When you look to the sky with a telescope. So the question is, why matter has a structure? And the answer to that is that structure is determined by fundamental interactions. Okay, so if we look in the very most simple case of a one-dimensional interaction between two bodies, you can have a situation like this. So these two bodies here interact by some interaction. And when they are far from each other, you have attractive forces. When they are too close to each other, you can have some short-range repulsive forces or centrifugal potential because of kinetic energy, something that prevents them to get too close, and you reach a stable equilibrium configuration. So this is what I mean by structure. Okay, so whatever interaction it is, you might have a stable configuration, and the stable configuration will be characterized by characteristic length and a characteristic energy. And this is what we want to measure. Okay, this is the most important thing we want to measure using X-rays and synchrotrons, is this characteristics, length and energy on matter. Because one thing that you can understand, if you measure this, you can infer about the fundamental interactions that created the structures. Okay, this is the same thing we do with telescopes when we look at the stars. So we look at configurations, measure distances, and we can infer about the interactions. Okay, so this is one of the reasons to study structure, to learn about fundamental interactions. Okay, and the other thing is related to function. This is well known in biology. Structure and function are strongly correlated, and also for materials as well. We have strong correlations between structure and function. And the example here is from graphite and diamond. So graphite and diamond have extremely different properties, microscopic properties. Graphite is dull, opaque, soft, and very common. Diamond, on the other hand, is brilliant, is transparent, It's very hard and it's very rare to find. And although they are made by the same atoms, exactly the same atoms, the structure, the configuration of the atoms inside is totally different. And this is what gives them the different properties. And different properties, you can exploit these properties of these materials to make tools with different functions, okay? For instance, you do a pencil with graphite, so something that is scratched by paper and it loses parts on top of the paper to write. And you can make something that scratches almost everything with a diamond, a tool that will scratch steel. So it remove parts of steel and not remove parts of itself. So you have these two extremes situation just by changing the arrangement distribution of atoms inside matter. So that's why we need to study the structure of matter. Function and properties depends on the structure. So knowing this, understanding the structure, we might understand the properties and better make materials with better tools with different functions. Okay, so this is why we need to study structure. And what's important is not only the structure of the atoms, but the structure of the electrons inside the atoms is also important. And here my example is still sticking with carbon. When you took graphene, it's this single sheet here of carbon atoms, and you put two graphene on top of each other, and you twist a little bit. So this was discovered a few years ago. It's a hot topic now in condensed matter physics. What's important is that if you change slightly this angle, you can observe extremely different emergent macroscopic properties on this same material. So the electrons behave totally different. They present ferromagnetism, they can present correlated insulator phases, ferroelectricity, and superconductivity just by fine changing the angle between these two sheets of the same material. So what happens is that when you change this angle, you are tuning the electronic structure. So you are changing this band structure of the electrons inside the material. So when you change the angle here in this animation, you show the angle here, and you see that when you have this these standard bands here that are is parabolic and almost linear here, and you change the angle, they become this flat band. And a flat band means that some of the electrons, they don't have momentum space to move around, so they interact strongly. So strongly interacting electrons that generate this emergent properties. So the picture that I want you to have in mind, the difference between a normal band and a flat band, would be this one here. Like a ballroom dance, this is the conventional band. So the electrons will behave almost like this. You have you have available momentum spaces. Flat bands is more like this crazy parties when everything is tight. This is the image for strong correlation, and you have this emergent, unexpected phenomenon happening. Okay, so think about that. So it's also important to probe the electronic structure of materials. You need to know the atomic structure and electronic structure to understand properties and new functions. Okay, so that's the take-home message from this talk. If you don't want to follow anything else, okay, but please have this in mind. Synchrotron is a good tool to probe the structure of matter. You can learn about fundamental interactions that are important to determine this structure, but also we can learn about the properties of materials and to discover new functions. So for materials innovation and fundamental understanding, that's why we're building these machines, and that's why they are so important. Okay, and the next step now is to understand a little bit what is synchrotron light. What is this? What's special about this light? So synchrotron radiation is just electromagnetic radiation produced from accelerated charges. Very similarly to what you have in an antenna that produces radio waves, you accelerate a charge, and you have this electromagnetic field propagating. The special case for synchrotron is that you have a relativistic charge being accelerated. So charges with velocities very, very close to the speed of light. When you accelerate this charge, so you change the trajectory, you emit radiation in a very different way. Instead of this isotropic emission, you have a concentrated emission in the very narrow cone in the tangent of this curve that you produce. And the radiation here has a very broad spectrum. So you emit radiation in several wavelengths and different energies, okay? An extremely high intensity because you concentrate all the intensity that was distributed on the very narrow cone. And it has also a very well-defined polarization, okay? That is the main characteristics for synchrotron light. So when you hear synchrotron light, synchrotron radiation, it's not a new type of radiation. It's just electromagnetic radiation. It's just a special way to produce. And the name comes from the type of accelerator that was just produced the first time with the synchrotron light. Okay, so we produce synchrotron light in particle accelerators to accelerate electrons in closed orbits. And when you make a turn, you change the trajectory of these electrons, they emit synchrotron radiation. Initially, it was observed as a parasitic effect. So they were accelerating particles to study high energy physics, collisions. So you're doing accelerator colliders. And they start to see these flashes of lights. Okay, this is the first observation here of the synchrotron light. Synchrotron produced by accelerated charges close to relativistic velocities in 1947 here. So since then, accelerator technology developed. So from the colliders, you see here, there's the Large Hadron Collider. This is the ultimate accelerator we constructed to study collisions in high energy particle physics. And accelerator technology also developed independently, more or less, for produce synchrotron radiation. In the very beginning, synchrotron radiation was used in machines that were dedicated for collisions. So you could, from time to time, you could go there and see what's possible to do with this light. From the moment it was realized that it was a good source for X-rays, UVs, and started the construction of dedicated machines, so dedicated accelerators to produce light. So you don't want to collide electrons or particles anymore. You just want to keep them rotating. That's why they call storage rings. So you just want to keep the particles rotating and producing light all the way, all the time. So you use the accelerator as a light source. And they evolved to what we see here now. So this accelerators at the beginning that you could hold in your hands, now they are large. And there's a special thing about this, what we call fourth generation light sources. That the Sirius is one of them. As I mentioned before, synchrotron light has a broadband, high flux, and it's small and collimated. And to compare different light sources, what we use is to characterize the source by their size and the angular divergence of the source. So comparing a third generation light source to a fourth generation, it's analogous to comparing a lamp, like a torch lamp, and a laser. So what you have in fourth generation light sources is that the size of the source is extremely small and the divergence is extremely low. So we quantify that in this number here that we call brilliance or brightness. So it's the flux divided by the size divided by the divergence of the source, okay? So we use this value brilliance to compare different sources. And now we can see here in this plot, this is in the vertical scale, here's the brilliance. In log scale, pay attention to how much it changes the brilliance. And here, different X-ray sources produced over the years. So a standard X-ray tube that you can see in dentist labs or research labs, they are more or less here in the 10 to the 8. First and second generation X-ray sources based on particle accelerators, the synchrotrons, are around here. This was our old source, was a second generation source. Has, okay, much higher brilliance than X-ray tubes, but you see that you can reach here for the third generation and fourth generations are up here. So we are orders of magnitude higher than what was possible, what was the brilliance of second generation sources. And you can see here that you reach what is called the diffraction limit. So this is a physical limit that we cannot increase the brilliance anymore. That's why sometimes these fourth generation sources are called diffraction limited storage rings. And the reason for that we have a physical limit to increase the brilliance, we have to look at what is the brilliance of a single electron. Imagine that we have a single electron rotating the synchrotron, and this single electron is producing photons. So there is a physical limit to how can you locate the position and angle that a photon is emitted. And this is related to uncertainty principle. So this product here should be small, should be not smaller by lambda for 4 pi. And this is what we call the emittance, this product of size and divergence for a point source. So this is the smallest emittance you can have. This is the natural emittance of the photon. When you construct a particle accelerators, their electrons, they have orbits that they go around this ideal orbit here. So at any point, you have a distribution of position and angles of the electrons. And this will make the emitted photons here to have a larger distribution as well in position and angles. What you have in Sirius and other fourth generation light sources is that the emittance of the electrons, so the position and angles of the electrons in the beam that is circulating the accelerator, is smaller than the natural emittance of the photons. So you are very close to this limit. For some energies, you are deep in this limit. Other high energies, you are not. But for part of the energies, you are in this limit where the emittance of the electrons is smaller than the emittance of the photons. Then you have a diffraction limit light source. That you cannot do better than that. Okay? And what I want to discuss is that this idea for a diffraction limited light source, it's relatively old. The first paper is from 1995. And it took almost 20 years for this idea to be implemented as an accelerator. This was the first fourth generation accelerator installed in Sweden. This is the Max 4 in Sweden. So why it took so long? And here is from Nature, I think it's 2013, that puts the light source that was under construction at the time. And the nice thing about this picture that I like to see is to see Brazil on Nature in a competing technology. So we are competing science with all the developing countries. So you have in the same diagram here from a Nature paper, Brazil is constructing a light source that will be competitive with all other developed countries. So why it took so long? So this is the question I want to answer. And it's not a problem of physics. The physics was well understood, but it's an engineering problem. Making this electron beam extremely small is very, very difficult. So it's not only a matter of knowing that we want to do this, is to actually making this stable, small beam in a very, very well-controlled orbit. So this is a chain reaction diagram for all the technical requirements you need to make this very small beam. So orbit stability should be extremely high. So this means that you have a stable building, air conditioning, and you need very fast orbit corrections to correct the small uncertainties in the orbit. The magnetic fields that guide the electrons should be extremely precise as well. The power supplies that feed this electromagnets should be extremely stable. You need high magnetic fields, so this means that the poles of the magnets should go very, very close to the electrons. So this means that the vacuum tubes, that's the electrons fly, should be very small, and it's very difficult to make vacuum on these very small tubes. So there are lots of technical requirements that took many, many years to overcome, not only in Sweden, but also here in Brazil. And after many years, we managed to do this. So we overcome this and we constructed Sirius. So I just want to show here a small video showing some of the, let's see if I can run the video. Well, unfortunately, I cannot make my video run. Okay, now. Now the video. This is the building. Was finished construction 1 year ago. Here's an evolution of the construction site from 15 to 18. You can see here the time is. Here's the construction of the accelerators inside the tunnel, inside this big building. So we have 2 accelerators, booster, the main accelerator here, and the linear accelerator on the back here. You can see there's the 3 accelerators that make the Sirius machine. Here's another view of the accelerators being constructed inside the tunnel. And finally, you can see the assembling of the experimental hutches where we will perform the experiments. So this is the main experimental hall here. This is where users come and make their experiments. Here is the tunnel where the particle accelerators are. And here's another view of the experimental hall. Okay, so where we assemble the beam lines and you put the instruments where you can put your sample and do your own experiments. Okay, now I just want to say a few words about how we can use X-ray to study the structure of matter. So just a few words about how the X-ray interacts with matter. So we have 3 main processes that happens in the interaction between photons and the electrons. One is the photoelectric absorption. This is the basics of the photoelectric effect. In this process, you transfer energy to matter. We have elastic scattering, where you change the direction of an incident photon. So changing direction means changing momentum. So we transfer momentum to matter. And you can also have inelastic scattering, where we transfer energy and momentum at the same time. So these are 3 limits on this for the interaction of X-rays and matter. And based on this different interaction processes, you can construct different techniques that are that there are several names here. You don't need to know the names, but are based on these elementary processes here. So what's important to know is that all of these three processes happens always at the same time, okay? With different probabilities that we quantify by these cross sections. And these cross sections, the probability that's proportional to the probability of these events to occur, they depend on energy and also depends on the atomic number. So that's why we can do imaging. That's why the absorption, the absorption cross section depends on the atomic number. That's the basis of radiography, okay? So some bones will absorb more than soft tissues. Okay, that's why we quantify, and this concept is we use this concept of cross section to compare these different probabilities of interaction between all these mechanisms. So you can perform scattering experiments where you monitor this momentum transfer. Here I'm showing just two extreme limits between a disordered and a crystalline solid, where you have this sharp peaks of the intensity of the scattered X-rays, and you can relate the position of these peaks to correlation lengths in your sample. So this is the limit of a highly ordered sample and a disordered sample. We have many things in between, different degrees of order that you can probe with X-rays. You can also do spectroscopy. In spectroscopy, you shine particles in your sample. You have this particle, these X-rays are absorbed. You might emit other particles, and you measure the energies. You measure the energies and the number of particles, and you construct a spectrum by plotting the number of particles as function of energy. And you can learn about elementary composition, chemical speciation, spins, and electronic structure. Depending on what you decide to detect. What products of the radiation matter interaction you decide to detect, you can have different spectroscopic techniques. And finally, we can also do imaging. You've heard from the talk before from Heloísa that one of the main things is projective imaging. You just have a contrast. You map the spatial variations of the absorption cross-section. So they change here because you have elements with different atomic number. We have these different contrasts. So the intensity changes. It's related to different distribution of elements inside the matter. You can also do tomography. So you do many projections and you reconstruct the 3D image of your material. You saw this before as well, so I'll not spend that much time explaining how you can see the 3D structure of matter using tomography. Okay, so and to do imaging, what you do in a microscope is to use a lens. So in our optical microscope, you use lenses. In X-rays, there are no good lenses for X-rays, so you need to do either scanning probe. So I make a very small focused beam, micro nano focusing, and I scan the sample. Or what I can do is to measure the scattering pattern of the sample, and I use a software, a computer, to recover the phase and construct an image. This is like what a lens would do in an optical system, but you use the computer to do this, to collect the scattered radiation and form an image. So what you do is you use a computer here with a model to collect this scattered radiation and reconstruct an image. And you can only do this micro focusing and this phase recovery if your radiation has coherence. And this is what is also very important for these fourth generation light sources. High brilliance give you high coherence, okay? And now to finish, I think I still have a few minutes. I just want to show some examples of applications in condensed matter physics. I choose a broad sense of condensed matter from the structure of liquids, soft matter, electronic structure of solid, and magnetic structures of solids. And I'm showing examples here I took from the literature. This is not my research. And I chose this because these are high impact research showing things that was done for the first time. And all of them were not possible to do in our old synchrotron. And these are things that we'll be able to do now at Sirius. So first is the structure of water. Water, from a perspective of a material, if you measure response functions like you do in solid state physics, compressibility and specific heats, the trend as function of temperature is completely different from normal liquids. So water is anomalous. This is known for many, many years, and it's known to be related to the structure of water. So there are many, and this is extremely important, right? The whole chemistry depends on knowing the structure of liquid water, the origin of life, and everything. So there are many theories behind the structure of water. One of these models is that this called the two-phase model, that water is in fact, liquid water is in fact fluctuating between two structural motifs. One that's called this high density liquid and the low density liquid. And when you look at the phase diagram of water, here at low temperatures and a relatively high pressure, what's called the supercooled water, you can have a phase separation. So you have a line here and a critical point. That above this critical point, you don't have more a very well-defined border between these two phases of water. So we might have strong fluctuations here. So you are in one phase, you have like bubbles forming of the other phase. And these fluctuations appear in these response functions that you can measure, right? The thermodynamic properties of water should reflect these fluctuations in this region here, which is called the widow line. So what this group of people here did on the science paper in 2017 was to measure this. So they use X-ray scattering to measure this correlation lengths in water. So you measure characteristic distances in water at long and short coherence and long coherence. I will not go into details, but what they see here is this correlation length as function of temperature. For each temperature in this supercooled limit here, you measure the correlation length and you also measure the compressibility. And you can see here at a very specific temperature, there is a peak in correlation length. And there's also a peak in compressibility. And this is experimental evidence of this widow line here, that above a critical point, you might have these fluctuations. Okay, so this is the first experimental observation of this widow line in the phase diagram of water. And they see here also when you change hydrogen by deuterium, you have a shift in temperature that's related to this the hydrogen bonding nature of the interactions, right, as expected. So the second example I want to show is the structure of lipids, in this case using inelastic X-ray scattering. So what you do is you shine X-rays in your sample. At a particular angle here, you measure the energies. So intensity as function of energy. And this is the plot here, similar to what Heloísa showed before in the inelastic neutral scattering. You measure intensity as function of energy. And this is very similar to Raman, if you're familiar too. So your X-ray can either lose energy to some phonons in these lipids or gain energy from the phonons. So we have longitudinal and the transverse phonon mode in this material, what these researchers found. And here's the dispersion of these phonons. So how the energy depends on the momentum. So you measure this spectrum here at different momentum transfer. So you look at different angles between the incident and scattered radiation, and you can map the dispersion of the phonons. And what's special about this work here is that when you change the temperature, when you go to this field dots here to the open dots, especially here in this transverse mode, you can see here that the dispersion disappears at a specific energy and momentum. And this is related to the gap in the phonon spectrum. And a phonon gap in this kind of materials is related to a localization. So what they can obtain from this kind of information is that you have like a pore opening. When you change the temperature here from 20 to 45, you have a phase transition that you go from this gel phase to the liquid phase in this lipid membrane. And this opens the possibility for these holes. This is the interpretation of the phonon gap. And you can use the energy, the specific energy and the specific momentum that the gap appears to infer about the size and the time scale for these holes. So these are dynamic properties of the membrane. So they are fluctuations. So that you can infer about the size and time frame for these fluctuations. And this was related to a transport mechanism, a passive transport mechanism in cells. So cells have this lipid membranes. And what they suggest in this paper is that this phonon modes, these collective modes in membranes could work as a passive transport. So things could go through these membranes during this short time. Okay, and this is also a very new word that appeared in the literature. The other example is about the electronic structure of the electrons inside solids, and this is also very nice work. Was published in 2015 in Science, and this is the observation of a vial fermion. So this is something that was predicted in quantum field theory a long time ago. This is a solution of some relativistic equation. The vial fermion was never observed as a fundamental particle, but it was predicted as emergent excitation in solids. So in some special solids where you have some band crossings, so excitations close to these band crossings could have the same physics as the vial fermion from quantum field theory. And this is the prediction from 2010 when they started to search for host materials for this type of physics. So the prediction was that in the momentum space of these electrons, there will be like nodes for the bulk electronic structure, and it would be related to surface. In the surface electronic structure, you would have surface states that are connected by these arcs. So this was the prediction since 2010. And they finally managed to observe this in 2015. And to see this, you need to look at the energy and momentum of the electrons. They have to measure that. And they use photoelectron spectroscopy, angle resolved photoelectron spectroscopy, that's called ARPES, in this material tantalum arsenide. So what they see here is, so this is the energy as function of the momentum. And if you measure this for different momentum, so different angles here, you can recover what is this called here, the Fermi surface. So this is the momentum distribution at zero energy. This will be like a cut in this cube here, in the z equals to 0. This is, and you see here they observe these 2 points that are related to this vial nodes here that was predicted experimentally. So this, to do this spectroscopy here, they used high photon energy, so they are bulk sensitive, and they also did the same type of experiments. So they measure the energy and momentum of the electrons for one particular direction, for one different momentum, measure for all over the crystal, so different momentum directions, and they recover the Fermi surface. So the surface, so the momentum distribution at zero energy. And you can see here you have this arcs here, this open structures here at the Fermi surface for the states here. This is the quantum states that are created only at the surface. So they managed to see also this structure here that was also predicted theoretically. And here, when they compare the two measurements, so these are measurements done at two different instruments, two different beamlines, and you can see here that the Fermi arcs, so this very nice structures here for the surface states of the electrons, they appear and disappear exactly in the same momentum positions where you observe the Fermi nodes on the bulk electronic structure. So this is the confirmation of this vial physics here in condensed matter physics. It's a beautiful example of what you can do with electrons. And just as my last example, I just want to show is that we can use also, we can probe the magnetic structure, so spins in materials. And this is also a very beautiful work that was published in Nature in 2017. And the idea is to look at the magnetization in soft magnetic materials. So in these materials, when you don't have a magnetic field present, the magnetization has a very, very complex structure. So you have domains and domain walls that have a very complex structure of the directions of the magnetization. And what they did was to use tomography. It's a special type of tomography called tachography to recover the magnetization in 3 dimensions. So let me explain this experiment because it's a little bit tricky. So they take this 5-micron rod of the cobalt gadolinium sample, and they shine with a nanoprobe X-rays, and they scan in the XZ direction. And for each point, they measure the scattered pattern. And they use a phase recovery algorithm to make an image. So this is the absorption image here. And they do this experiment at 2 polarizations of the incident light. So circular polarizations with different orientations, like right-handed and left-handed. And when you do the difference, you can have an image with the contrast is proportional to the projection of the magnetization. So in this image here that I'm showing, dark and light represents magnetization that are parallel or anti-parallel to the incident beam. Okay, so you can have an image of the magnetization. So what they do is do tomography now. So they rotate 360 degrees, measure all this images with magnetic contrast, and they incline the sample and do it again. So doing this long procedure, what they can do is to resolve in 3-dimensional a vector field. So they resolve the magnetization, so the direction of the magnetization in 3 dimensions with a resolution of 100 nanometers. So this is extremely difficult to plot. So what I'm showing here is a cut in this small rod, and you can see here the flow lines. So it is easier to see a vector field using flow lines. And there are some very special points here. You see that's you circulate or you diverge. So these are these special points called Bloch points. So this is like domains wall in 3 dimensions. They find each other in these small points here, and they have these extremely different configurations. You can see in 3 dimensions here. So this is the plot of the magnetizations. So this is the component in color here is the component of the magnetization in the vertical direction. So it changes color. So you have this one domain and this second domain here for the vertical component. It's very hard to plot a 3D vector field. So you need to look at projections and to see the arrows at special locations. So what they show here is 2 special locations here where you see these Bloch points, where the magnetization have these very different configurations. And this is important because it was the first time that a magnetic was solved inside a material in 3 dimensions. So there are a lot of theories to explain these blow-up points, but was never experimental evidence for that. Okay, so it's unique, and it's what is possible to do with X-ray imaging in these new synchrotrons. So to conclude, I want to go back to this first slide that I showed, that synchrotrons are very good to probe the structure of matter. You can understand the fundamental interactions, and also it's important for materials innovation. You can learn about properties and function of new materials. And to finish, I want to give this, leave here this message from Rosalind Yellow, that new truths become evident when new tools become available. And my final message is that the synchrotrons are open source facilities. So SIRIUS is an open source facility. If you want to see more information, just visit our website. You can see here, any user can just apply for a beam time. And what I want to call your attention here is that SIRIUS receives the first experiment users. So we are running, and we have some experiments working at the moment, and soon many beamlines will be open to users. So just collect your samples, collect your ideas, and be prepared to come to SIRIUS. So if you want to have more information, you can always talk to me. And thank you for your attention.
Thank you very much, Túlio, for this really interesting talk, and especially to show how broad is the range of application and the range of kind of properties that we can achieve to get with this tool. So it's really, really amazing what we're able to have. So we have, so again, you can raise your hand, either raise your hand or use the question and answer. And we have first a question from Victor Lima. Hi, Túlio, nice to see you. Thank you for the excellent presentation. Could you talk a little about the temporal resolution available at some SIRIUS beamlines? And will the IPE beamline will also be able to perform experiments with temporal resolution?
Okay, first of all, in general, the electrons inside the accelerator, they have a time structure. So the electrons, they are packed in bunches inside the ring. So the radiation that comes out of the ring, they also come in bunches. So the X-rays has a bunch structure that's on the order of picoseconds. So we can use this as trigger to do some time resolved experiments. So this is possible in many synchrotrons. And at higher time scales, you can always follow dynamics up to picoseconds. And lower than that, there are some possibilities to have information on dynamics, but not looking time domain, but in energy domain, as Heloísa mentioned before. So IPE, we can do spectroscopy, in elastic X-ray spectroscopy, that can have some information on the dynamics, so how things change with time, but looking at the energy domain. So it's similar to measure in the X-rays, in the momentum space, and infer about the real space, looking at in the Bragg peak. So the width of the Bragg peak, you can correlate to the size in real space. So similarly, if you look some broadening of some peaks in an elastic spectroscopy, you can infer about dynamics and the time dynamics.
Perfect. So it's possible, but it's not the easiest to.
No, there are better tools for that are being developed, that are the free electron lasers. So this you have time domain spectroscopy, time domain scattering, direct information.
Perfect. We have another question now from Diego Guzman. He said, thanks for your presentation. I have a curiosity. How can we select the energy of the electronic radiation that will go to the different lines of light of the synchrotron?
Oh, very good question. So we have a broadband source, and each beamline, we specialize in an energy spectrum. We use a device called monochromator. It's very similar to a prism that disperse visible light, but we exploit the different interaction of X-rays and matter to construct these devices using crystals and diffraction gratings that can also disperse the radiation, X-rays, and we select the energies that we want. So this is a very good question. So we have special optical devices for X-rays, not only to disperse, but also to focus, to collect, to shape the beams.
So each beam lines can choose what will be their energy without.
Exactly. You can work on the infrared, in UV, in low energy X-ray, high energy X-rays. So you choose the part of the spectrum that you want to work.
We have another question still from Diego. What is the type of polarization of the electromagnetic radiation? Does it depends on the beamline? The polarization.
Yeah, it depends a little bit. Also, beamlines tend to specialize. So this depends on the type of the source that you use in the synchrotron to produce the radiation. Some sources you can produce only vertical. Other sources you can produce only horizontal polarization. But there are some special sources called elliptical undulators or delta undulators that you have full polarization control. And this is what we are planning for many of the beamlines, and including the one that I work, we have a source that allows full polarization control, vertical, horizontal, in any angle, and circular polarization.
We have now, you get a new user, a future user. So Lincoln, thank you for your presentation, very didactic. Good to know that Sirius is open to Brazilian research samples. So soon you will
Hope to see you soon. So more and more beamlines are becoming online. We are doing technical commissioning and receiving some users already.
That's really good news, and yes, it's for us, for Brazilian, especially for us to be able to get access. I have one question, because Sirius is really amazing what we will be able to get for the experiment, but from the engineering point of view, it's also amazing that we were able to build all this. So can you comment on what was the main technical challenge for the building, the engineering, the design, and the building?
Yeah, so there are many challenges, and this is so Sirius as a whole. I like to see there are three different scientific instruments: the accelerator, the building, and the beamlines. These are three sets of different equipments that have to work together under very tight specifications. We had challenges in all of them. Starting from the building, there was no company in Brazil that could make the floor stable enough. There was no technology here. No companies could do that. So it was the same also for magnets, for the power supplies, and for hutches and monochromators, everything. So this was something very nice about this project, that we worked together with several companies in Brazil. So 80% of the whole budget of Sirius was spent here in Brazil. And we had this transfer of technology. We have to make the prototypes here together with many companies so they could learn and produce themselves, because it's an industrial scale. We could not produce everything here at the lab. So we need the companies around Campinas and in different places of Brazil to take part on that. So I think this is one of the best things about the project, is how you qualify and use this industrial infrastructure of Brazil. And there are many challenges. From vibrations of the building, you need to make pillars that are 11 meters long, deep inside the soil to stabilize the floor. The floor has to be a single piece of concrete. The building has to be extremely tight temperature control inside the tunnel. You cannot have fluctuations by 0.1 degree, and you see how much temperature changes here in Brazil. So air conditioning was very difficult, very expensive. Power supplies as well, magnets. So there are many challenges, and I think this is overcoming these challenges with the partnerships with different companies. I think this. Together with the new science is, I think, the best thing of this project.
Perfect. So, well, thank you again for your nice presentation, for explaining. Yes?
Can I make a question?
Oh, yes.
I'm sorry. So, Túlio, thank you again for the presentation. It was really nice. And it showed me also a point that I talk a lot with my students, that you don't need to have an area of research to do research. I guess that all physics is really interesting, and it's open for all kind of questions. And two things that caught me my attention, because I'm from field theory. So when I saw that slide that you show of the vial fermions, I was really surprised, because I didn't know that that it could be observed in this context of condensed matter structure. And also, I would like to ask if you can do the same thing for Majorana fermions too, because they were not observed as single particles, if you know something about it. And another question is that, or in fact, it's a comment, is that that domain walls that you also show in the end of the presentation, they are just like some solutions that people use
exactly
to map orbits of many bodies systems, like Poincaré section. So they are much like Poincaré section. So this was also very interesting, because have applications in chaos studies and something like that. So thank you.
Well, many comments. First of all, this solutions of quantum field theory in condensed matter physics in many body physics is a hot topic. There are people are searching for Majorana in topological superconductors. So surface states of topological superconductors, I think, are the best candidates for the Majorana. Axions as well. So they are searching for some host materials for axions, and even black holes horizons. There are some propositions that you can, because of this duality with quantum field theory and some gravitational theories, you might have be able to have a condensed matter many body physics or many body system that mimics the black hole horizon. So follows the same physics, the thermodynamics of a black hole horizon. So this is active, and this is things that we can measure. So if theoreticians, if you have good idea or any proposition, just talk to us. We try to find somebody to synthesize the material and measure these properties. Now we have the tools to measure this, the electronic structure of these complex materials. So we just need good ideas and good samples to make this kind of research here in Brazil.
So really interesting. So yes, it's not only for experimentalists, also for iteration. It's really, really powerful. So thank you again for your presentation. And I will thank both speakers actually to show that big facilities and X-ray or neutrons are really be able to get inside the matter, and it's really interesting for us. Just the imagination, we need imagination and see if it's feasible or not. So I thank both Túlio and Heloísa again. And now I guess it's the coffee break, and the session will continue at 11.
Thank you. We come back 11 o'clock.